Hey, my name is Benjamin Schumann, and in this fourth video I want to talk about how to use an external library to implement pathfinding on top of the AnyLogic network that we have now and on top of the agent-based implementation of that. Remember, AnyLogic gives you pathfinding with their built-in network, but it's always the shortest path, and you lack basic controls of how pathfinding should be done. You also lack the interactive element that our agent-based approach gives you. So in this video, we will use a new library that gives you full control over pathfinding, and we will implement and connect it to the agent-based setup that we've got. Let's get started. The library that I have chosen for this example is called JGraphT, which is one of several pathfinding Java libraries. It seems to be very well supported. It seems to be quite recent, quite accurate. It seems to be very well used. So that's always a good sign. It's open source. It's got a lot of positive reviews. So you could say it's a good way to get started. There are also others like Jung, but this one, for example, hasn't been updated for over 10 years. So I'd be careful. So JGraphT is an external library, and it allows you to do lots of things with it. It has full documentation, has a user guide, but essentially what you need to do is you need to download the actual library file. Then in AnyLogic, in your model, you click on the actual model properties, not an agent or anything. And in there you get a list of the jar files, Java archive files, that are required to build the model. And our model needs two jar files, the JGraphT core library, and it also needs, for some of the code, the JHeaps library that comes with the JGraphT library. So in your case, if you don't use this model, what you have to do is download this zip file, unzip it, and then click on this little green plus button, browse to your download folder, and select the JGraphT and the JHeaps file. Make sure you say to import the file to the model folder, so then it's part of the model and you'll never lose it again. When you do this, as soon as you do this, you now have the full power of the JGraphT library. So if I just do code complete here, I can already see there seems to be some JGraphT stuff available now, which was not available before. So once we've done this now, let's understand how pathfinding and graphs work. First of all, AnyLogic decided to use a different wording than normal pathfinding libraries. In AnyLogic, what we have is we have this whole thing which is called a network. And a network is made up out of nodes and paths, where the nodes can be three types. They can be rectangular nodes, point nodes, and polygonal nodes, as we've seen. Now, in the pathfinding community or research area, this is actually not the notation that is being used. The notation that is being used over there is different. In their world, the whole network is called a graph. A node is called a vertex, and a path is called an edge. So from now on, I will speak clearly, and when I say path, I mean the AnyLogic path that is part of the AnyLogic network. When I say vertex, I mean the graph vertex that has an equivalent of being a node in AnyLogic. So what does it look like? Classical graph theory is its own research area, and it has lots of good algorithms for finding shortest path or any kind of path through a network. Through a graph, sorry. And a graph, as I said, is made out of vertices and edges. That's all there is to it. Now what we will do is we will translate the AnyLogic network into a JGraphT graph. How do we do this? First of all, it's basically three steps. I create a variable called vgraph that is of a very specific type. It's called, in this case, direct weighted pseudograph, but we could also make it a lot simpler and just call it a simple graph. Like this. This is also a very simple graph provided by JGraphT. Now, why do we use this really complex word for a graph type? Well, JGraphT being, a library that is not developed for AnyLogic, particularly, it's a huge, a very powerful program. It allows you to specify lots of different graph types or graph structures, as they call it. If you check out the help, you'll see all the graphs that you can actually build with JGraphT. Now, why did I choose directed weighted pseudograph? Well, let's break it down. The graph that we want to build from the network has to have certain characteristics. For example, the edges in our graph need to be directed because some of the edges will have a direction. We want to be able to utilize that feature and force directions on some of the paths, whereas other paths, edges will be bidirectional. So our graphs need to be directed, meaning it needs to be one of those. No undirected edges. Let's look at the weighted column. We want to be able to have full control over path finding, so we want to be able to apply a weight to each edge, basically saying you can go across this edge, but it's going to cost you a lot more, or the weight will be a lot higher than if you use other edges. This could translate to all sorts of things. It could be the distance being used as a weight. It could be a price. It could be the quality of the road. It could be all sorts of things. You can basically translate anything into a weight. So we want to have a weighted edge. So we're down to these 4 options down here. Now let's look at multiple edges. That basically means I want to be able to create a graph where I have more than one edge exiting or entering a vertex. So this node in AnyLogic has 2 paths leaving it. And in the JGraphT equivalent, we want to have this as well. So we need to have multiple edges. So it is down to these 2 options now. And the last decision that we need to make is, do we want to have self loops? Meaning, do we want to be able to draw a graph where we have a path like that leaves one vertex and returns to the same vertex. Now, while we don't have this here in this one, we want to be able to do that. In reality, we might have networks with that characteristic, so let's go for that as well. And this leaves us with a direct weighted pseudograph. It is basically the graph that can do anything. Now, this means that the path-finding algorithms will be a little bit slower, but for the kind of purposes that we are doing here, it's trivial. You don't need to worry. If you build buildings or road networks or any kind of thing, where you don't have millions of nodes and millions of edges, you'll be fine. Don't worry. But if, you can always change this. You can make your graph to be of a different type. Directed weighted pseudograph. And we need to provide 2 things. We need to provide what are the vertices going to be represented by. And in this case, I'm explicitly saying the vertices in my graph should be node agents, A_node, i.e. it can be rectangular nodes, point nodes, or polygonal nodes. So JGraphT knows that nodes are these type of things. Vertices are these type of things. And it wants to know what type will the edges be. And we are basically here taking a JGraphT data type, the default weighted edge. It's just an edge that has a weight. But you could turn this, you could actually say this should be an A_path. There's nothing hindering you and telling JGraphT the edges should be path. Go for that. Fully okay. So when we start the model, this is just an initial empty graph with nothing in it. Now, as you remember, we call this function fCreateNetwork. And this function does 2 things, and we've explored one. We've explored how it instantiates agents and turns the network into an agent-based representation. Now we look at the second thing. In parallel, it also fills the graph with nodes and vertices now. How does it do it? Again, we loop through all nodes in our network and create those agents, but also just one line of code. We tell the graph to say, please add a vertex to yourself. Which vertex should be added? The current node agent, a_node agent that we've just created up here. Either rectangular, point node, or polygonal node. That's all we are doing. So at the end of this for loop, our graph will be full of vertices, but no nodes yet, so no pathfinding possible yet. For adding edges to the graph, we also utilize our for loop where we go through all paths in the network. But it's a little more involved than just one line of code, because if you think about it, when you create a path, when you create an edge in a graph, the edge needs to know two things, three things actually. Where does it start? i.e. from which node does it start? To which node or vertex does it go? And in which direction? So the direction is implicit because it goes from A to B, and we are using a directed pseudograph. So all edges are always directed. We do not have bidirectional edges. It's always from one to another. And the third thing is you can add a weight. So we loop through each path and we get the path. Now, when we want to add an edge to the graph, we need to know where does it start, where does it come from. So what we do is for the path, the network path that we have, we grab the start node of that path. The path itself in the network has a function getSource, which gives you the network node where it originates from. We translate that to the actual node agent using our own little function here, which basically just loops through all the agents. And we do the same with the end node. The network path has a getTarget function giving you the node at the end of the path, and we translate that to a node agent. Now, what does start and end actually mean? If you have a path like this is bidirectional, it still works because it accounts for how did you draw this path. If I click on this bidirectional path, you see there's still an arrow going from left to right, meaning I drew this from left to right, and this is the source, this is the target. If I unclick it, the arrow is gone, so this is the indication, this is only in the background. Whereas this path here, you see the arrow is always drawn, indicating to you that it's a bidirectional path, but it's also from the left origin to the right target. So now we have the start and end node. And now all we have to do is, again, one line of code. We go into our graph and say, please add an edge from the start node to the end node. And we just store this here temporarily. Because not only do we want to add the edge to the graph, but we also want to set the weight of that edge. And here you can go all out. This can be as complex as you like. The simplest case is that you just use the path length as the weight, which will make pathfinding in this graph a distance-based graph finding. And if we ask for the shortest path, it will literally be the shortest distance through the path. Now, we said that edges always are one directional, but what if in the network, like here, our path is actually bidirectional? You have to manually create another edge in the opposite direction in the graph. There's no other way to do that. And so we do that. And that's absolutely fine. There's nothing hindering you that's a standard procedure. So what we do with the next bit of code is, well, here we create the path. We've talked about this, but now we're checking, is this path actually bidirectional, the path that was drawn? If so, we actually add another edge to the graph that now goes in the opposite direction from the end node to the start node. We set the edge weight to exactly the same weight, just the distance, and that's it, off we go. And with this, remember this is just trace lining stuff. With this bit of code now, we have a fully defined JGraphT graph. And if we run the model, and instantiate our graph. Let's go into the model agent and click on the JGraphT. We do see that it has lots of stuff in it, and you can, improve the toString method if you like, but it's all there. And if you would call or uncomment this traceline stuff here, you would get a nice printout of all the vertices and all the paths in the network, who is connected to whom and what does it look like, and you'll end up with a theoretical representation of this network. Now, how do you do this path finding actually? This is only step one. We've instantiated and created a graph. Now we want to use it. And this is semi-simple. It is simple from a JGraphT perspective. For actually using it as an agent-based model, there's one little trick that we need to do on top. The simple JGraphT bit is just 2 lines of code. We instantiate a Dijkstra shortest path variable. This is a JGraphT object that gives you the shortest path through your graph using the Dijkstra algorithm. There are a ton of other algorithms. You can do whatever you like. It's JGraphT. You're fully flexible. In this case, I'm just using Dijkstra because it's like the de facto standard for path finding. Check out on advantages, disadvantages yourself what you actually need. What we do is we instantiate a new Dijkstra on our graph, and then we can ask that object to get us the path, the shortest path between some origin node and some target node. And these must be A_nodes now. Not objects, but they have to be actual A_node agents, because that is how we defined our graph. So now we can actually work with the agents. And having that path, we can query it. Like, what is this path? How do I get from the origin node to the target node? And you can query it by getting the vertex list. That is a sorted list of the vertices that you need to move through. So if you want to move from here to here, it will be a list of this A_node, then this this little point node, then this point node, then this point node, and so on until you arrive at your destination. And the other thing you do is you can get the edge list, a sorted list of all the edges that you need to visit sequentially. And this would be the edge represented here, and the edge, this edge, and then this edge, and so on. Now the disadvantage is that we cannot get a sorted list of vertex, edge, vertex, edge, vertex, edge to visit. We need to build this ourselves, because this is what we actually want to give our agents. They should be able to know, oh, this is the vertex where I start, then I go to this edge, and then this vertex, and so on. So building that sequential list of markup elements is the little trick that we are doing on top here. I'm creating a linked list. Normally it would be just a linked list of network markup element agents, i.e. nodes and paths. Remember our agent hierarchy. But there's one additional twist where we need to specify the direction. So we make it a pair where each network markup element has a true or false Boolean or null. We'll get to that. Now, how do we combine these vertices and edges? We loop through all the vertices and create one entry, one pair for that vertices, for that vertex that we're currently at. We set that Boolean value to null because it's a vertex. We'll get to that. And add it to our linked list. But then after each vertex, we also check if we should squeeze in an edge as well. So it's always, you always have vertex, edge, vertex, edge, vertex, edge. There's no different way of doing it. So we can code it like that, where we get the edge that is currently after the vertex that we've just had. We get the path agent represented by that edge. And now we also want to tell the agent, the pathfinding algorithm only tells you, you need to move through this edge. But it doesn't tell you in which direction. It is implicit in the pathfinding because it goes from this node, or this vertex to this vertex. But to tell our agents that, we need to make it explicit. And we'll come to that in the next video. but the agent needs to know, should I move from left to right or right to left? So to make it explicit, we pull out that bit of information by comparing where does the edge start, what is the vertex of its source, and comparing it to the path represented by that and its origin node agent. So we don't need to go and don't need to understand the details of this. This code really works well and is quite robust, but essentially this tells us, does the edge move forward or backward? And we fill another pair with the current edge and flagging is it's forward or backwards. We add it to the list of sequential elements, and with that now we have a list of vertex and edge steps that an agent can visit sequentially, and if it is an edge, it will also know if it's forward or backward. And then all we do is give that to the agent, but this is what we'll look at in the next video. But the actual pathfinding is very simple. It's just 2 lines of code. You create a shortest path object, and then you get the vertex list or edge list from an origin to a target. As simple as that. And then you do with it whatever you like. Alright, so in the next video, we'll talk about how do we actually use this for agent movement. I hope it was helpful, and I'll see you in the next video.